Quantum software gets the attention. Hardware makes it real. And hardware is not one thing. Three major architectures are racing toward the same goal: fault-tolerant quantum computing, superconducting circuits chilled near absolute zero, trapped ions floating in electromagnetic fields, photonic qubits riding pulses of light. Same destination, totally different engineering. Today we compare how each design works, who is betting on it, and which path looks strongest in 2026. Start with the design most people picture: superconducting qubits. Tiny circuits cooled inside dilution refrigerators. Temperatures colder than outer space. Google, IBM, and Rigetti built empires on this approach. The advantage is speed. Gate operations in nanoseconds. Chips fabricated with modified semiconductor tools. Scaling looks like adding more units to a lattice. The disadvantage is noise. Coherence times stay short. Everything fights heat and electromagnetic interference. In 2026, superconducting teams lead on qubit count demos and fast gate research. They are the sprint car of quantum hardware: fast, demanding, constantly tuned. Now the precision players. Trapped ion systems levitate individual atoms in vacuum. Lasers manipulate their quantum states. Coherence times can stretch seconds to minutes, far longer than superconducting qubits. Gate fidelity is often excellent. Quantinuum and IonQ are the names you hear most. The trade-off is speed. Gates run slower. Systems are harder to scale to thousands of qubits on one chip. But for error correction research and certain algorithms, that fidelity buys time. Think of trapped ion as the surgical instrument. Slower hand movements, cleaner cuts. The wild card: photonic quantum computing. Qubits encoded in light. PsiQuantum and Xanadu chase this path. The dream is familiar fabrication. Optical components instead of extreme cryogenics. Room temperature operation in parts of the stack. Massive scale through photonic integrated circuits. The challenge is loss. Photons disappear easily. Creating and maintaining entanglement at scale is brutal. In 2026, photonic teams raise huge capital and publish ambitious roadmaps. Fewer live qubit demos than superconducting leaders. But if loss engineering cracks, the manufacturing story changes overnight. Here is the scorecard. Not qubits alone. 1. Gate fidelity, how often operations fail. 2. Coherence time, how long a qubit stays useful. 3. Connectivity, can every qubit talk to every other or only neighbors? 4. Error correction overhead, how many physical qubits per logical qubit? 5. Manufacturing path, can you actually build 1 million of these? Superconducting wins on speed and ecosystem size. Trapped ion wins on fidelity and coherence. Photonic wins on theoretical manufacturing scale. No architecture wins on every line. That is why the race stays open. Honest standings. Superconducting platforms dominate cloud access and published qubit scaling milestones. Google and IBM set the pace most headlines copy. Trapped ion vendors lead select fidelity benchmarks and enterprise partnerships. Quantinuum and IonQ show up in chemistry and optimization pilots. Photonic players lead fundraising narratives and long-term scale promises. PsiQuantum builds fabs. Xanadu pushes photonic quantum computing software. Neutral atom and silicon spin approaches lurk as dark horses. The leader depends on the metric you care about. Scaling count today. Fidelity for correction tomorrow. Manufacturing cost at commercial scale. Your move. Pick a metric before you pick a winner. If you care about cloud experimentation today, superconducting has the most doors open. If you care about correction-friendly fidelity, watch trapped ion progress. If you care about fabrication at scale, track photonic loss breakthroughs. The architecture war is not winner-take-all. Different designs may own different niches. Chemistry here, networking there, optimization somewhere else. Tune in tomorrow. We cover quantum cloud platforms, where you can actually run these machines in 2026 and what each portal is good for. Subscribe if you want the future without the fluff.